In this problem, we're asked to replace the loading system shown in the figure by an equivalent resultant force and couple moment acting at point A. So I'm going to approach this problem by first calculating the equivalent resultant force that is the combination of the 900 Newton and 300 Newton force, and then calculate the equivalent couple moment acting at point A that will take into account the moments created when the 900 Newton force and 300 Newton force are moved to A. So I'll start with finding the equivalent resultant force. The x component of the equivalent resultant force is just going to equal the sum of the forces in the x direction. And the 900 Newton force has an x component, which is equal to 900 sine 30. The 300 Newton force has no x component, so the x component of the resultant force is 450 newtons. The y component of the resultant force is going to be the sum of the forces in the y direction. The 900 Newton force has a y component has a y component that acts downward. Now I'm using my standard, that's horrible. I'm using my standard reference system, just remind myself here. So the y component of that 900 Newton force is minus 900 cos 30. And the 300 Newton force is going to be minus 300. The y component of the resultant force, therefore, is minus 1079.4 newtons. Now draw my force parallelogram, or rectangle in this case, since I have the orthogonal components of the resultant, and the x component is 450. This one's y component is 1079.4. The resultant of those two components is shown here, f sub r acting at an angle theta, and I can calculate f sub r by finding the square root of the squares of the two components. So it's 450 plus 1079.4, or f sub r equals 1169.5, which will round to 1170 newtons. So that's the magnitude of the resultant force. The direction of the resultant force is going to be given by theta, which is inverse tan 1079.4 over 450, or 67.4 degrees. And remember that theta is acting, the force is acting downward and to the right, so theta is measured from the x-axis there. Okay, so the equivalent resultant force, here's its magnitude, here's its direction, and we would show that at A. As a matter of fact, let's show it at A. So I would show a, let's do it in a different color here. Let's do it in orange. So the equivalent resultant force is 1170 acting at an angle here of 67.4 degrees. Okay, so that's F sub R. Now I'm going to calculate the resultant moment about A. And here's where I will account for the moments created when I moved the 900 and 300 Newton forces to A and found their force resultant. So let's look at the 900 Newton force first. I already have the two components of the 900 Newton force. The X component has a line of action that acts through A, so it creates no moment about A. The Y component, I'll put them up here. The Y component acts at a perpendicular distance of 0.75 meters from A. So the moment of the Y component of the 900 Newton force is going to be its magnitude, which is 900 times cosine 30, and then the perpendicular distance is 0.75. So that's the moment of the 900 Newton force about A that we have to account for because we move the 900 Newton force, its line of action, to A. So it acts through A. And we need to determine the sign, the SIGN here of this moment. We said that counterclockwise moments are positive. So if we look at that, the moment of the Y component of the 900 Newton force about A, we see that it's clockwise, which makes it negative. Okay. Now let's look at the 300 Newton force. When we move that to A, we have to account for 300 newtons times the perpendicular distance, which is 3 times 0.75 meters. That force also makes a clockwise moment about A, which is negative. And now we have to account for the free moment of 300 Newton meters. And as we talked about in the lecture, we can move a free moment anywhere with not having to account for the distance or anything. But we do need to know what direction that moment is acting in to know whether to add it or subtract it here. So it's acting counterclockwise, so we're going to add that 300 Newton meters. So we do that math, and we get that the resultant moment about A is minus 959.6 Newton meters, which means that it is acting in a clockwise fashion. So we could leave it like that, or we could show it as, and we'll round at the same time, 960 Newton meters clockwise. So there's the resultant moment. It's clockwise, so we can just show that here as a moment about A that's acting clockwise that has a magnitude of 960 Newton meters.